Welcome. We are looking at the explicit method with the periodic boundary conditions, and we are having some difficulties in getting the solution. So, I have noticed a couple of errors. So, I am going to go through the script once more and let us fix the errors and then run the code. So, we have the figure clear and then clear the all data that might be there, and delta t is 0.01 and delta x is 0.5, d is 1. So, alpha is defined as d times delta t by del x squared, it is 128, and because del x is 0.5, m should be equal to 2. If you do not take m to be equal to 2, because del x is 0.5, you are getting just 1/2 of the sine curve that we saw, right. We are seeing that the composition profile looks like that instead of looking like that. This half is missing because we are taking a delta x of 0.5 as we see here. If you take delta x of 0.5, then n becomes 64, and so we should take m to be equal to 2 to get 2 waves. Okay. So, that is the first error that I noticed. The rest are okay except for one small typo which is hard to catch. It took some time for me to figure out. So, in this for I equal to 1 to n, I just wrote I to n. Okay. So, that was an error, and that is the reason why there was no evolution of the composition profile. So, I have corrected these two, the rest of the script is as usual. So, we have the initial profile defined and then initial profile plotted with red stars, then hold on, and then this is the loop for plotting, this is the loop for time evolution, this is the loop for evolving in space, and we define west and east point, which is I minus 1 and I plus 1, and the west there is no 0th point. So, if you reach a 0th point, that is for the leftmost point, the first point when you look at the west point, we are going to assume that that is west plus n, and if you are at the rightmost point and you are looking to the east point, there is no east point. So, we are going to subtract n and take the first point to be the east point for the last point. Okay. So, this is periodic boundary condition, and then we evolve the composition and we take the old C, the current C as the old C, and then we go through the loop, and after that time loop is over, then we plot the composition and then end the plotting loop, and then we take the figure as explicit PBC.tps. Okay. So, let us run this code. So, I am in the right directory in which I have invoked Octave, that I can check. So, present working directory, it says desktop teaching phase field. So, and I can also list the files that are available. So, I can see that explicit periodic boundary condition 1D diffusion dot octave is available. Okay. So, I am going to source that file. Okay. So, what we are expecting is that because we have a sinusoidal profile like this, all right. So, what we are expecting is that because this has a curvature like this, at these points the composition should come down, because this is 0 curvature, it should remain where it is, and because this has a curvature which is positive, I expect the composition profile to go up here. So, whatever extra material that is here should come here, right, and then it will go like that, and then finally it will reach this point. As you can see, that is exactly what the solution of Octave looks like. So, the red points are the initial profile that I had, all the blue lines, there are 20 of them, they are all corresponding to the composition profiles at different times. And as usual, I mean, of course, this is the point where there is no composition change, because the curvature is 0 at that point. So, it is not going to change at all, and near these points. So, wherever the gradients are high, there is the composition change is larger, and wherever the gradients are smaller, the composition changes are also much smaller. So, you see this nice curve that you get, indicating that the fixed second law says that compositional heterogeneities will be evened out. This is the homogenization solution. This is the meaning of fixed second law. Fixed second law says that the rate of change of composition at any point depends on the curvature of the composition profile. If the composition profile has positive curvature, in those points the composition is going to rise, and if the curvature has is negative, then in those regions the composition profile is going to go down. So, in the process any noise or any modulation you have can be thought of as to be consisting of positive and negative curvatures. So, they are all going to get evened out. So, this process is going to stop only when the curvature becomes 0 everywhere. So, you have a flat line, you have a straight line parallel to x axis. When composition is not changing with position at all, that is when this process is going to stop. So, this is the solution. We had difficulty in producing this. Initially we had just one half like that, and that did not evolve at all. So, that is because of the errors that I noticed and showed you now. Thank you.